So we have an ICS alum who works at Autodesk, and I'll introduce Erin in a second, and then you're going to hear from one of the ICS faculty who does some, at least tangentially related work in simulation and design. So let me first bring up Erin Bradner, as I said, ICS alum and a research scientist here at Autodesk, who's going to talk to us a little bit about what goes on here. Thank you, Erin.
Okay, so I'm Erin Bradner, and I had to look at my badge to remember what year precisely I graduated. I graduated from the ICS department 2001, and at that time it was CORE. If anybody, I hear some chuckling back there, so somebody recognizes that acronym. And thank you so much, Dean Stern and Dean Washington. I really love seeing the two of you together and the engineering department and the computer science department together, because we've been talking about convergence. And in fact, I am living convergence. And what I mean by that is engineering and computer science, engineering and architecture, engineering and manufacturing, design, converging. So it is no longer plausible for an engineer to create a design, throw it over the transom to fabrication to manufacturing, and have that manufacturing process be played out without the involvement of the designer. These two fields are converging. In architecture, we see prefab construction on the rise, such that a building is no longer a foundation that is poured and then sticks that are erected with 2x4s. It is a building that is assembled on site. So we talk about, for example, the Apple campus. If you've been watching that campus evolve, it's a neat project to take a look at. But our CEO talks about that as being an open air factory. So it is not about building the building after it's been designed, but it is about fabricating and assembling the construction. I will be talking to you about a project that I'm actively working on called Generative Design, which is intimately associated with additive manufacturing. So generative design is this notion of designing with algorithms. No longer is the CAD designer simply specifying points, lines, and surfaces in a CAD tool and transcribing the idea that he or she had in their mind into a digital drafting tool. Now, and in the future, the CAD designer, the designer, will be specifying their goals and constraints and recruiting the computer to algorithmically derive designs, and not just one design, but multiple design alternatives that satisfy those constraints. That is generative design. I work in the Autodesk Research group here in San Francisco. So this is a algorithmically derived bike. And I was having a conversation here earlier, I think Andre, you were talking about a bike that does not need a stem or does not need a stay in the back. And it does not if you algorithmically introduce the variations and say, in fact, to our algorithm, which designed this bike, there is an obstacle here. Don't grow there. What I like about this very simple example is that, and we did this about a year and a half ago, is that some of these bikes, let's see, not that one, that one, that looks like a bike I have in my garage. Some of them do not, in fact, look like a bike I would have in my garage. And that is I think one of the opportunities from the human-computer interaction standpoint and the cognitive science standpoint, that the algorithmic approach is going to offer you solutions that were highly counterintuitive. How are we doing that? Well, one thing we're doing is capitalizing on multiple trends. One is cloud computing. So high-performance computing that's available and accessible to all designers. In fact, our CTO, Jeff Kowalski, said, what is the practice of design going to look like when every designer has a supercomputer at his or her disposal? And that is, in fact, what is available now to designers, but largely what we're seeing the cloud used for is as a massive storage cabinet in the sky. It's not used for its computing power. So what we wanted to do is capitalize on that compute power of the cloud. We also wanted to capitalize on additive manufacturing. This is a failed print, and I intentionally showed you a failed print because that is a lot of what's happening is we're able to theoretically produce any complex form that the designer can design, but once it gets to print, it fails. So how do we capitalize on the promise of additive manufacturing on these infinitely complex designs with the aid of infinitely smart, intelligent software? So that's the other thing we wanted to do. And the third is use algorithms and machine learning to aid the designer. So those are the three trends that are underpinning this approach in generative design. As I said, generative design is recruiting algorithms to assist the designer. So what I want to do is give you a very simple example. This is a bow. This bow here was designed by an artist in residence. So we have artists who we bring in to use our software. They can use our off-the-shelf software or our research software. This artist was not a bow designer. He was an amateur archer, and he said, you know what? I've seen your generative design demo, something we demoed internally because it's not a commercially available tool yet. It's a research prototype. And he said, I want to do a bow. I want to design a bow. So what he did is he scanned his arm holding his bow, the bow that he currently has. This is called a recurve bow. So the dynamic energy is absorbed here. This is a structural member. And he scanned his arm. He brought that into our prototype software for generative design. This channel, can anybody guess what this channel might be? I mentioned no grow zones.
That's an arrow slot.
Right. So it's a channel that the arrow needs to pass through. These pesky little things, I need to have a screwdriver be able to assemble this or build this pin in. So these are obstacles in our model. In the fullness of time, we'd like to be able to just assign those as no grow zones. But this is an immature algorithm. So we have obstacles. We have interfaces. So these are the interfaces where it's interfacing with this dynamic member here. And we have forces. So this is what you would call a 25-pound draw. So we know the forces on this object. And this was the design that the algorithm produced. And it produced that through a topology optimization approach. But I use that term reluctantly because topology optimization is known to mechanical engineers as a method to reduce weight. And it is always started with a seed design. I have done the CAD, and now I'm going to take it into an optimization algorithm to remove weight. So this is not how our algorithm works. We, in fact, simply say, interface here, withstand this load, here and here, now synthesize from thin air. So that's how the algorithm works. It produced not just one, but multiple, and it happens to be a commercial product now, the bow, because an artist designed it, and it's the first design out of the system. So that is our bow. And let's see. So I wanted to communicate that these algorithms are not just producing one, but they're producing multiple designs. So what you see here is a bike stem. And simultaneously, we've told the algorithm, all right, produce the design in steel, produce this design in aluminum, produce this design in titanium. What would it look like? Produce this design in polycarbonate for 3D print. What would it look like? So the algorithm is producing multiple design alternatives at once. Here is a drone body. So we said, look, there are 4 forces operating here where the propellers mount. There is a gravity load of the battery and the camera. What is this drone body going to look like? And this is just one of the many solutions that it produced. So let's say I'm designing a motorcycle swing arm. Have you ever seen a swing arm that looks like that? That is the algorithmically derived swing arm. I just need to identify the obstacles and the forces, and the algorithm will derive that design. Now, there's more than one way to synthesize the design. I've got a supercomputer. Why don't I try multiple synthesis methods? And I can do that and arrive at different designs. In this case, we were exploring with multiple materials. Down here it's titanium, and frankly it looks very anemic to me from an aesthetic standpoint. Up there it's polycarbonate, and I don't think I want to ride a motorcycle with a polycarbonate swing arm, but you get to see the range of solutions that the algorithm arrives at. This is a car chassis. This car chassis was designed by a designer specifying the forces. Now, what happens if you take a car chassis and you take a prototype, you sense it, you drive it, and then you take that sensor data and you bring that into the algorithm? What is it going to look like? So in this case, it's doing a topology optimization. That's one form synthesis algorithm. It's finding that shape, looks very organic, very bone-like. And then we decide to use that as a seed for a truss algorithm. So that truss algorithm is placing nodes and placing beams, and it's synthesizing that form in a arguably more lightweight form. And we can synthesize that and specify the material to be aluminum, to be titanium. And we're simply using the material definition, the Young's modulus, and the Poisson ratio for those. So that has been experimentation. This is a partition, an interior partition, a cabin partition for the Airbus A380 to be tested over the next few months and to be flying by the end of the year. It is generatively designed, algorithmically selected among a large competing set of solutions. And it was printed, 3D printed, using a custom material called scalum. A shoe. You can order this shoe now from Under Armour. And I take you from aerospace to athletic apparel, just to give you a sense for the range of artifacts that are being produced currently using a generative design approach. So this was done with our commercial grade generative design software called Within. And the point I want to leave you with is, again, instead of the designer taking one design that they have conceived of as brilliant as it is and transcribing that to a CAD tool, they are defining their goals and constraints and allowing the system to offer up a range of solutions, a Pareto front, if you will, of solutions that they can then navigate, explore, curate, and select as a seed to continue iterations or to pull out and then fabricate. And that's why I'd like to leave you with generative design. Thank you so much.
Thank you, Erin. That was fantastic, really quite amazing. We have time for a couple of questions if you want to ask. Yeah, that's fine.
So are you selling this to other engineering companies as a tool to be able to get rid of design?
Right, are we selling this? So the tool that you saw here is a research prototype that is not commercially available. The tool that was used to design the shoe, for example, is commercially available. It's on the Autodesk product list. The reason the tool that I demonstrated to you is not yet commercially available is simply because it was an experiment and then we realized the commercial value of it, and we're working diligently to commercialize it. It will likely be componentized and put into our standard product offering as a generative design feature or feature set.
Amazing.
Thank you.
Yeah.
Hi.
This is really fascinating stuff. So I was wondering if you could talk about the software a little bit more. So it sounds like there's some training that's happening. Is this sort of AI based?
No training. So it is There is a algorithm that is synthesizing the form in much the way bone grows. So it will reinforce, it will deposit material where there is force and remove material where there is not. But it is not taking a machine learning approach. It is not analyzing a set of design alternatives and then either creating a new alternative or synthesizing an alternative. It is growing that form. And we plan and are actively working on using machine learning approaches to meta-optimize, to select that synthesis method that's appropriate for the problem, and then possibly to seed the designs with existing designs. But that was our intention was not to take a machine learning approach at the beginning. It's to synthesize the design from scratch.